Hello there. My name's Meza Tovar. I'm a graduate student in the Earth Environmental Science Department here at UT Arlington. I'm going to be presenting my research, which is on the mechanism of temporal variability of vertical distribution of density in Reservoir Lake Arlington. So this reservoir is positioned in a subtropical region, meaning hot summers and mild winters, so it sees no ice coverage at all. This lake is a crucial source of water for three cities. It is used for cooling of a power plant and recreational activity such as fishing and boating. So this lake is considered a eutrophic lake, meaning it's relatively rich in nutrient concentration and sees high biological activity. This lake isn't that large, only spanning a surface area of 7.8 kilometers square and only reaching a maximum depth of 15.6 meters. With that, it is considered a warm, shallow monomictic lake, meaning a certain part of the year sees distribution of oxygen and nutrients, and it's evenly distributed throughout the lake's depths, and this is usually seen from fall to winter. And to really accurately depict this, we try to figure out the temporal variability, and we utilize Heinz-Steffen's one-dimensional quality model here in my model description. And he starts off with a basic heat diffusion equation, which is the partial derivative of temperature over time, and this is equal to the K, which is constant diffusion coefficient. Next, we make that K a depth-dependent eddy diffusion in lakes. So K is now added to Z is now added to that K, and AZ is now incorporated, which is the area of Lake Arlington at a certain depth. With that, everything on the right side is now considered the heat flux change with depth. Building upon that, we now move on to equation 3, which is incorporating external heat source. So this is H divided by PC. H is the internal heat source due to solar radiation, P is the density of water, and C is the specific heat capacity of water. Lastly, we move on to equation 4, which is my current equation, and it's heating source by the power plant. So we add QPP to this, which is the thermal input from from the local power plant. So this is QPP, and this equals delta T over K, which is the observed temperature change in Celsius over a time constant for the process. Really, to get all this, we do weekly samples, and in my methods, we attempted to, I can show you this, and we tried to go weekly out to Lake Arlington, but we were limited to weather, wind speeds, and vehicle maintenance. With that, we did use the YSI Pro meter, which helped me figure out temperature, salinity, dissolved oxygen saturation, and concentration at different depths. My Milwaukee BEM 802, which captured surface pH, electroconductivity, and total dissolved solids. Lastly, I used the Secchi disc, which helped me assess the water transparency and to estimate light attenuation in Lake Arlington. Oh, well, each time I went out. With that, I recorded meteorological data. This includes air temperature, wind speed, wind direction, precipitation, solar radiation, and cloud coverage, and other factors like dew point. With all these measurements and data, I started building a groundwork in MATLAB for this one-dimensional model, and started really analyzing all this data and creating time depth matrices. With this, we can see this in my results. Let's start off with figure 1. This is my seasonal variability in Lake Arlington. And the top one is going to be my average temperature. Middle one is reservoir storage. And the bottom one is wind speed and direction. So these were taken from September through April, well, through last week, because I didn't go out today. So with that, we move on to figure 2, which is my temperature diffusion plot. So this is the one-dimensional model that I'm working on, and these are my initial results. And I'm basing this off an average temperature from September to March. So of course, we don't have the annual temperature, so this is not going to accurately depict it, but this is a working process. Next, we move on to figure 3. So figure 3 is my time depth plots. So I do have temperature, dissolved oxygen concentration, or I'm sorry, oxygen concentration, and apparent oxygen utilization. So I was able to get an average of 11 meters throughout the year. So this is kind of how I worked out the matrix. And then again, with all this, these are measurements from September through March. So really to wrap this up in my conclusions, So once I complete this 1 year study, I should be able to fully develop this one-dimensional model. And this is going to help me predict, or not predict, help me with the uh, understanding the complexity of lake dynamics and temperatures over time, as well as different factors and laying the foundation for the understanding of subtropical lakes. Hopefully, I'll be able to apply this to another lake like Joepul Lake and in my future works. So once I complete this full year model in September, or full year of testing and measurements in September 24, I hope to complete the seasonal cycle model. And I want to move on to different stuff like the dissolved oxygen dynamics and apparent oxygen utilization, and really applying the same diffusion or one-dimensional model to these different factors. With that, I think that is all my time, and I would like to thank y'all for watching this video. I hope you have a wonderful day.